Hello everyone. This is Chi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Hello everyone. Welcome back to our Deep Learning course. Today, we're wrapping up Chapter 5, Classic Convolutional Neural Networks, 5. Part 5.5, Tips for Data Augmentation. Data augmentation is a super practical technique in deep learning. Let's learn what it is, how it works, and apply it to the cat and dog classification task we did earlier. First, let's clarify what data augmentation is. It's often translated as data enhancement or data augmentation. The core is to increase the size of training samples by applying various transformations to the original data. For example, stretching, rotating, or flipping an image creates new samples. Importantly, data augmentation is another common and powerful technique in deep learning, right alongside batch normalization, BN, we learned last time. When training deep models, especially CNNs, we often lack enough labeled data. Data augmentation solves this by reusing existing data to create more training samples, which helps reduce overfitting. Why does data augmentation work? Let's start with the difference between how humans and computers process images. For humans, if we stretch, rotate, or flip a cat image, we still recognize it as a cat. For computers, every transformation turns the image into a new pixel matrix. The computer sees it as a new sample, not the same one. The catch is, when we convert an image to a matrix, the form computers understand, some valuable information is lost, like the invariance of an object to rotation or scaling. Data augmentation helps make up for this loss. By creating transformed samples, we teach the model to ignore irrelevant changes like rotation and focus on key features like a cat's ears or a dog's nose. The slide shows common transformations: zooming 2x or 0.5x, rotating 30 degrees, shearing, shifting up or down or left or right, and flipping. These are all easy to implement with Keras. Let's apply data augmentation to our cat and dog classification task. First, we create the test set generator. Note, we don't augment the test set, we want to test on real data. The code is similar to before. Set im size equals 128, same as last time, to keep consistency. Use image data generator, rescale equals 1/255, only normalize pixels to 0 to 1, no other transformations. Read from a/data underline, BN or catdog or validation. Resize to 128,128, batch size 200, class underline, mode equals categorical, 1 hot labels. This generator ensures the test data stays original, so we can fairly evaluate how well the model generalizes. Now, the key part, creating the training set generator with data augmentation. We add multiple transformation parameters to image data generator. Shear underline, range equals 0.5, applies stretching transformation, shear, to the image. Rotation, range equals 30, rotates the image left or right by up to 30 degrees. Zoom, range equals 0.2, zooms the image in or out by up to 20%. Width, shift, range equals 0.2, shifts the image horizontally by up to 20% of its width. Height, shift, range equals 0.2, shifts the image vertically by up to 20% of its height. Horizontal, flip, equals true, randomly flips the image horizontally, for example, left-right flip for a cat. We still read from the train folder, with the same size and batch size as the test set. This generator will automatically apply random transformations to each training batch, turning our original training data into a larger, more diverse set. To see what the augmented images look like, we visualize 10 samples from the training generator. The code is simple. First, use x, y equals next, train underline, generator to get one batch of augmented training data. Second, create a 2-row, 5-column figure, set height 6, width 15 for clarity. Third, Flatten the axes and loop through 10 images. Axi, show xi displays each one. The slide shows the result. You'll see some images are rotated, some flipped, some zoomed, but you can still tell they're cats or dogs. This confirms the augmentation is working. The model will learn from these varied samples, making it more robust. Next, we build a CNN model for the augmented data. We'll combine it with batch normalization for better performance. First, input layer, input imsize 3 128 multiplied by 128 color images. Second, initial BN layer, x equals batch normalization, x stabilizes input data. 3.7 rounds of conv pool, loop 7 times, add ABN layer conv2, d, n underline, channel, 2, padding equals, same, activation equals, relu, 100 kernels of 2 multiplied by, 2, max pooling, 2d, 2, downsizes by half each time. Fourth, flatten and output. Flatten, converts 2D features to 1D, dense 2. Activation equals, softmax, 2 units for cat or dog. Finally, model. Summary prints the full structure. This model is deeper than the logistic regression one we used before, and the combination of BN and data augmentation will help it train better. The slide shows the model structure diagram. Even though we can't see the exact details, we can infer from the code. Each round of BN conv pool reduces the feature map size, for example, 128/60, 432, until the final pooling output while keeping the channel count at 100. The flatten layer converts the final pulled feature map into a 1D vector, which feeds into the fully connected output layer. Total parameters will be higher than the simple logistic regression model, but the deep structure and augmentation will let it capture more complex features of cats and dogs. This structure balances depth and efficiency, perfect for our classification task. Now, we compile and train the model. Compile, use model. Compile optimizer equals atom LR equals 0.0001, loss equals categorical underline, cross entropy. Metrics equals accuracy. We use a smaller learning rate, 0.0001, because the model is deeper. Atom optimizer is still a good choice, and categorical underline, cross entropy, fits multi-class binary here classification. Train, use model. Fit underline, generator, train underline, generator. Epochs equals 200. Validation underline. Data equals validation underline. Generator, train for 200 epochs. Data augmentation means more diverse samples, so we need more epochs to learn and validate on the test set. With data augmentation and BN, this model should have higher accuracy and less overfitting than a model without augmentation. Finally, let's go through the exercises to consolidate what we've learned about data augmentation and classic CNNs. List at least 3 image-based classification problems, for example, flower classification, car model classification, and briefly describe their inputs, images, and outputs, class labels. Linet 5 is classic, but its settings, like convolution kernel number or size, layer count, can be modified. Try changing them and see how model accuracy changes. Choose one dataset, use logistic regression as a benchmark, and compare its accuracy with other CNN models like Linet 5, AlexNet. Add batch normalization to CNN models that don't have it yet, and observe if accuracy improves or worsens. Think, in the 5.52 cat-dog case, what would happen if we didn't use data augmentation? Hint, likely more overfitting, lower validation accuracy. Take your time to practice. These hands-on experiments are the best way to master deep learning. If you have questions, feel free to ask.